and you're in my class. This is the makeup module that replaces your lowest module activities. And so in case you're wondering what that means is that this module has, just like all the other modules in this class, 3 different components, which is the discussion, the activity, and a quiz at the end. And you can choose to do any one of those 3 or all 3 of those activities. And each one will replace your lowest discussion if you do the discussion. It'll replace your lowest quiz if you do the quiz. And it'll replace your lowest activity if you do the activity. So that's really what this is. And really what this module is going to be about is about weather forecasting. So it's something that I don't talk as much about throughout the rest of the course, but it is still a pretty interesting topic, and it is still something that is worth investigating if you have the time to do it. So with that said, let's jump in. This first part, which I'm calling Lecture A, is the steps to making a good weather forecast. And you can find this in Chapter 9 in the textbook if you want to follow along in the textbook. And let's do it. So, before we even begin, I should stress that weather forecasting is very much predicting the future. Very similar to how you have a fortune teller looking over a crystal ball and trying to predict your future, trying to say, okay, well, this is going to happen in the future and this is going to happen. Well, weather forecasting is essentially that. In a very real sense, we are trying to look at how weather conditions are going to change in the future. Now, how do we do that? What is our crystal ball? Well, there are 2 steps to making a good weather forecast. And the 2 steps are making a diagnosis and making a prognosis. If you've ever been to the doctor before, they will give you these 2 things, a diagnosis and a prognosis. The diagnosis tells you what the problem is. The prognosis tells you what's going to happen next, in a sense. And so weather forecasting is very much the same thing. The first step, before we can make any kind of forecast, we need to assess the current situation of the atmosphere. That's what the diagnosis is. We need to gather weather data telling us what the current state of the atmosphere is. Then, based on the current state of the atmosphere, we can take that data, plug it into numerous models. Each one has different skills and different things that they do that then give us a forecast. And then humans take that forecast and interpret it to then determine what the weather is actually going to do during that time. And so by the time that weather forecast reaches your TV screen or your cell phone app, it's gone through this process. It's gone through the process of diagnosing current conditions, taking those current conditions, plugging them into a model, and then evaluating the output of that model. So really, before we can even make an accurate weather forecast, we have to accurately collect data. And this is one of the reasons why all of the different data collection standards I've talked about in this class, all the different data collection techniques that I've talked about in this class are important. Because if we can't accurately collect weather data, we can't make an accurate forecast. So if we can't collect accurate temperature data, if we can't collect accurate wind speed data or accurate precipitation data, then whatever we end up with as far as a weather forecast is concerned isn't really going to make sense. Now, luckily, we have many tools available to us to both access current weather data and calculate future predictions. Now, assuming that you aren't a field meteorologist and you're not actually out on the field collecting the data, you just want to know where you can retrieve it. Now, the good news is even for the armchair meteorologist, or for just a casual meteorologist or a student, accessing weather data is really easy to do. There are numerous sites and numerous agencies that make weather data readily available free of charge. These include the National Weather Service, which is the United States Weather Agency, the World Meteorological Organization. This is an international body of the world's top meteorologists, and MesoWest, which is the agency that I personally like to use to access weather data. Now, once you get this weather data, there is a ton of different components to it. You have temperature, wind speed, wind direction, cloud cover, precipitation, and each one of these things are being measured at different heights in the atmosphere and different locations. And therefore, you've got this 3D data set that is overwhelming with all these different variables. And so it can actually be really difficult for a human being to sit down and make sense of that data. Well, luckily, not only do we have tools to retrieve the data, we also have tools to interpret the data. One of those tools is what's called the AWIPS. AWIPS stands for Advanced Weather Interactive Processing System. And what this system does is it allows forecasters all across the nation to organize and use all of their data. And if you take a look here, this looks like a computer nerd's dream. You've got different screens with all kinds of different displays of data on them. You've got an upper level chart over here. You've got a coastal ocean chart over here. You've got a water vapor chart here. And with AWIPS, you're able to organize and easily access all of this data. So instead of just being given a table of raw data that would be overwhelming, you can switch back and forth from one data set to another, from one location to another. And this makes forecasting a little bit easier. Other tools include what are called meteograms. A meteogram is basically a 24-hour graph that shows you how all the different weather conditions have changed over a 24-hour period. I pulled this one from San Jose International Airport, and what it shows you here is in this top panel, you have temperature and dew point temperature. So this is air temperature here, dew point temperature here. Down here you have visibility. Right here you have wind information, and if you recall from the station model, you have wind direction, that's this long barb. Wind speed, that's this little stick that points out of the long barb. And then the circle is filled to a certain degree based on cloud cover. This image down here shows you different cloud heights where they're present. And then this right here shows you air pressure. And different meteograms can show you different conditions. You can see precipitation on one. You can see other things such as how much precipitation. But this is basically a one-stop shop for all of the weather information for a given location. Now, another tool that we use that you've actually seen in this course is what's called a STUV diagram. STUV diagrams give us weather information not just at the surface, but higher in the atmosphere. And what it gives us is it gives us information such as air temperature, that's this line on the right, dew point, which is this line on the left, parcel temperature, so this is what would happen to a parcel of air as it rises, in this little gray line here. Meanwhile, over here, this shows you how wind direction and wind speed change with height. And each one of these conditions can tell you a lot about what's happening in the upper layers of the atmosphere. And they can also give you indications of if the atmosphere is stable, unstable, what layers of the atmosphere are moist, and hence clouds are present there, what layers of the atmosphere are dry, hence no clouds, what wind is doing with height, how it's changing with height. This can also tell you a lot about different types of advection. If the winds change a certain direction with height, or what are called veering or backing winds, they could tell you a lot about advection, whether warm air, cold air is moving in, and so on. And so these are very useful tools. Now, we combine all of these tools, and we combine all of the data that we gather from these tools, and we put it into what's called a computer model. Now, we've talked about models in this class a little bit already. A model is a simplification of a real-world thing, such as a model airplane is a simplified version of a real airplane. A model of the atmosphere is a simplification of the real-world atmosphere. And so these models are very useful because they take away many of the very inconvenient and difficult to deal with complexities that make weather forecasting hard to do. And instead, all that you're left with are pretty basic equations of the atmosphere. You then plug the data that you have into those equations, so you plug the current temperature into those equations, the current wind speed into those equations, the current air pressure into those equations, and then those equations are then calculated and they spit out a forecast. And the way that computer models do this is they run these equations not just over one large area, but they take that area and they split it up into many different smaller areas called grid boxes, also known as cells. And for each one of these grid boxes, a forecast is created. So for each one of those grid boxes, a forecast is created. Now, with this said, there are a few problems with computer models. First off, these boxes would need to be infinitely tiny in order to give you a perfectly accurate point forecast. But the smaller they are, the more equations that need to be run, because you're running equations for this box, this box, this box, this box. The smaller the boxes, the more of them you have. The more of them you have, the more these equations have to be used. And you're not just doing this for the surface, you're also doing this for higher layers in the atmosphere. So that creates a big issue. Another big issue is that these equations, because they're simplified, they're not a 100% accurate representation of the real thing. Just like a model Boeing 747 isn't a perfectly accurate representation of a real-life Boeing 747, these models of the atmosphere are not 100% representations of the atmosphere. As a result, all the things that have been left out can come back to bite you. And so that's another problem with computer models. With that said, the more we understand our atmosphere, the better we're able to parameterize these assumptions and these uncertainties, the more accurate our models have become. I'll talk more about that in a moment. But before I do, let me go back to talking about these grid boxes again. These grid boxes represent something called resolution. And there are two types of resolutions. There are what are called spatial resolutions and temporal resolutions. Spatial resolutions are the size of these grid boxes. The larger the grid boxes, the lower the resolution. And we'll talk about why that's such a big deal in a few moments. On the other hand, a temporal resolution is how often are you going to make a forecast? And when you make a forecast, the way that the computer model works is it uses the current weather conditions and it uses them to then make a forecast for a certain time out. And in a high-resolution forecast, it's going to choose a short timeout. So it's going to choose maybe 5 minutes from now. How's the weather really going to change between now and 5 minutes from now? Some drastic things can happen, but they're not going to be incredibly drastic. So usually the 5-minute forecast is extremely accurate. And then that forecast is then fed back into the model to make a forecast for the next 5 minutes. And then that forecast is then fed into the model to make a forecast for the next 5 minutes. And then the next 5 minutes. And then the next 5 minutes. Until you have a forecast for your desired time. Now, in a high-resolution forecast, this time period is going to be smaller and smaller. A 5-minute forecast is a pretty accurate, pretty high-resolution forecast. However, many forecasts, rather than forecasting 5 minutes out, they forecast an hour out, or 3 hours out, or 6 hours out. And a lot can change in the atmosphere between now and 6 hours from now. And so those lower resolution models aren't nearly as accurate. So with that said, there are two types of resolution: high resolution and low resolution. High resolution forecasts use very small grid boxes and very small changes in time. So again, in this case, you're forecasting the weather conditions for a tiny area, and you're forecasting them over a tiny period of time. As a result, they're extremely accurate. But the problem with these kind of resolutions is this means that you have to run those equations hundreds, thousands, hundreds of thousands of times over. So they take forever to do, and they also require a tremendous amount of technology available, a tremendous amount of infrastructure. This isn't something you can just do on a laptop computer or on your iPhone. This is something that requires what are called supercomputers to do. And even with a supercomputer, some of the world's top computers, it could still take hours to make a 24-hour forecast with a high-resolution forecast. On the other hand, if the resolution is lower, this means that those grid boxes are larger. So instead of representing a few miles, they may represent a few hundred miles. And that change in time, instead of it being every 5 minutes, it's going to be a longer change in time, such as an hour. Now in this case, you're not running those equations nearly as many times. You're not using up as much energy. You're not using up as much computer space. These forecasts are a lot easier to do. And many of these kind of forecasts you can do on your computer. You can do on your iPhone. They don't take long to do. But they're not nearly as accurate. Because a lot can change in the weather over a longer period of time. Like I said, not a lot can change in 5 minutes. A lot can change in an hour or 3 hours. And a lot can change over 100 miles. Think about here in the San Francisco Bay Area. The difference in the weather between here in San Jose and up in San Francisco is oftentimes profound. Or if you jump over the hill and you go to Half Moon Bay, the difference in the weather between here and there is usually very profound. So you get a big difference over a small distance. And so these higher resolution models give you better detail and better accuracy, but again, they take forever to do. A good visual example of this is compare a low resolution image of the Mona Lisa where every grid box is given an average color, and what you see here, and the grid boxes are very large. What you see here is a pretty hard to read image. You can kind of still pick out that it's the Mona Lisa, but you really don't get a pretty good feel for it. Whereas the higher resolution, these grid boxes are infinitely small, and so you can see subtle differences from one place to another, and you get better detail. Now, as I mentioned a few minutes ago, not only are we making weather forecasts for different grid boxes at the surface, we're also making them for key layers above the surface. And the reason why is because what we see in the upper layers of the atmosphere can tell us a lot about weather at the surface, especially when it comes to forecasting weather. And there are different layers that we as meteorologists look at. I've written these layers down here, and these are the primary layers. There are other layers that we look at, but these are the primary layers. Obviously, at the surface, we're looking for surface conditions, things such as what the temperature is, what the wind speed is, what the humidity is. And at the end of the day, this is what we ultimately care about as people. But this is greatly influenced by what's happening aloft. And so we look at other layers, such as 850 millibars. This is the layer in the atmosphere where pressure is 850 millibars. Here, we look at things such as advection of moisture, temperature, and what's called the low-level jet. The presence of this low-level jet can indicate whether we could expect severe weather or not. Then at 700 millibars, we specifically are looking at advection. If we see warm air advection happening at 700 millibars, that's going to indicate warming temperatures near the surface. So looking at advection aloft can tell us what's going to change at the surface. Then at 500 millibars, we're looking at something called vorticity. And vorticity tells us a lot about the presence of high and low pressure systems, the presence of ridges and troughs, and vorticity can also tell us a lot about lift in the atmosphere. Places where air is rising in the atmosphere and places where air is sinking in the atmosphere. And then finally, the 300 millibar level gives us a good picture of where the jet stream is located. Now, we look at these things not just for the current conditions, but we do forecast them out in time as well. And what we get back as a result is something called a prog. A prog is a map giving us a prediction or a prognosis of the weather. So I mentioned in the beginning of this lecture that a prognosis is basically just a prediction. It's what's going to happen next. And so these 24-hour progs give us a prediction of what the weather is going to be like 24 hours from now. And we get these progs for all of these different layers of the atmosphere. Here at 300 millibars, these areas of orange and red represent the jet stream. Here at 500 millibars, these represent areas of higher vorticity. Here at the 700 millibar, this indicates the presence of different moisture. And here at 850 millibars, this gives us things such as the low-level jet. So we look at each one of these layers to get a feeling for how the weather is going to change in them. Now, every model is different. There's no one universally used weather model. And the reason why is because to take all of the perfections of different weather models and to get rid of all the imperfections would create a model that can't be used. It would take too long to run. It would require too many resources. It's just impossible to use. Sort of in a way like, let's take a college for example. So in a college, you don't have one person who teaches you all of your different subjects. So for example, I'm your meteorology teacher. I'm not going to be teaching you English. I'm not going to be teaching you history. I'm not going to be teaching you math. I'm not going to be teaching you physical education. You're going to go to different people for those things. We are what are called specialists. I am a meteorology specialist. I specialize in weather. Your English teacher is going to specialize in writing. They're more skilled in writing than I am. If you came to me for writing advice, I would defer to them. And the benefit of this is that each one of us can focus on our specialties. I don't have to worry about memorizing MLA format. Instead, I can focus on better understanding meteorology, so I can better teach it to you. Well, in that same tone, every weather model has a different specialty. And as a result, every weather model has a different resolution. It uses a different set of equations and it uses those differently. And it has a different set of assumptions and approximations. So every weather model gives you a different taste of what's happening in the atmosphere. Now, there are many different commonly used weather models. Here in the United States, the three that we use are called the NAM. This is the North American model, the Global Forecasting System, or the GFS, and the European model, the ECMWF. And each of these models give us different perspectives of what is potentially going to happen in the atmosphere. One of them may do a really good job at forecasting temperature. So when we look for temperature forecasts, we look at that model. Another one may be really good at forecasting precipitation. We are going to look at that model. Another one may really do a good job forecasting the presence of high and low pressure systems. We then defer to that model, and so on. And then there are also private weather models. And these models are designed by industries that just focus on what they need. So, for example, if you're a wind power forecaster, if you need to know how windy it's going to be in your area so you know where to point your windmills or which windmills to have on, well, you don't really care about the air temperature outside. You don't really care about the precipitation outside. You really only care about the wind speed. So you're going to use a model that specifically focuses on creating wind speed. And you're also going to work hard to perfect that model. And so that becomes your own private model. And so every model's different. Every model has different strengths. Every model has different weaknesses. Now, with that said, when models agree on something, that's usually a pretty good thing. So, for example, if you came to me and you asked me a question and I gave you an answer, then you went to your English teacher, asked them the same question, and they gave you the same answer. Then you went to your history teacher and asked them the same question, and they gave you the same answer. Chances are the answer is probably correct. It's probably a very believable answer. Well, in meteorology, when models agree with one another, that is a really good sign. In order for us to figure this out, though, in order for us to figure out, do these models agree with each other, we have to run what are called ensemble forecasts. An ensemble forecast is simply a weather model that's run many different times with slightly different initial conditions. So we take a weather model and we tweak something about the data that we're feeding into it. Either we tweak the temperature slightly or we tweak the wind speed slightly. And we look at how that affects the weather forecast. If the output of each one of these models still is in agreement with one another, then we have what's called a high confidence forecast. In that case, even despite the slight differences, they all still agreed with something at the end. So again, as I mentioned, that's just like what would happen if you asked me, your history teacher, your math teacher, and your English teacher the same question, and we all gave you the same answer. you can now be confident that that is probably a correct answer. And obviously, the more people you ask and the more you get the same answer over and over again, the more confident you can be. Now, on the other hand, let's say you came to me and I gave you one answer. You went to your English teacher and they gave you a different answer, and you went to your history teacher and they gave you a different answer. Well, in that case, we each gave you very different results. In that case, the answer is low confidence. Well, in the case of meteorology, when an ensemble forecast comes out as with very different results, so those slight tweaks in the initial conditions result in very different results, confidence becomes very low. Here's an example of a high confidence forecast. This was for Hurricane Sandy. And Hurricane Sandy was forecast to make a very unusual turn on the eastern seaboard. Normally hurricanes like Sandy start down here, they travel parallel to the coastline and out to sea. Well, Sandy was forecast to, instead of doing that, it was forecast to then make a turn back towards the east coast. Now, in this case, we ran many different models. We ran the NAM, we ran the GFS, we ran the ECMWF, we ran all kinds of different models. Each one of those models is indicated using different shades. And we ran them with different initial conditions. And if you take a look, for the most part, almost all of the models forecasted that turn. And almost all of the models gave you a pretty good idea of when the turn was going to happen and where Sandy was going to hit. As a result, we were able to confidently say days in advance, hey, Sandy's going to make this turn, the people in the Northeast better watch out. That's a high confidence forecast. If you take a look, almost all of the model results agree that, hey, Sandy is going to, it's right down here, it's going to make this turn back to the East Coast. On the other hand, here's an example of a low confidence forecast, specifically further out. Initially, all of the models are in pretty close agreement to one another. However, the further out you get, you notice that each of the models is giving you a very different result. Some models are forecasting 850 millibar temperatures as high as 25 degrees Celsius, which is a little over 70 degrees Fahrenheit, while others are forecasting it to be as low as 2 to 3 degrees Celsius. That's roughly 32, 33 degrees Fahrenheit. And you see a very wide spread, and it looks very noisy. In this case, we can't make an accurate forecast because the model results are all over the place. This indicates a situation where the forecast is low confidence. The ensembles gave us very different results. And even though we can average those results out to give us a mean forecast, the fact of the matter is that this mean forecast is really just the average of a bunch of junk. So we really don't get anything useful here. And since we don't get anything useful here, we can't make a really accurate forecast long term. Instead, we say that this is what's called a low confidence forecast. Now, one other tool that meteorologists use with models is they look at what's called model output statistics. Model output statistics are a little bit different than what I just showed you because rather than showing you weather conditions over a large area, model output statistics give you progs for a single location. And rather than giving you all of the progs, they give you just 3 hour, 6 hour, 9 hour, 12 hour, 15 hour, and so on progs. And they give you progs from different models. They give you progs from the GFS, progs from the NAM, and so on. And these are a good way of taking all the model results and packaging them up in a tightly, easy-to-use system. So for example, what this can show you, first off, it gives you the date up here. Down here it gives you the local time. Actually, I think this is time in UTC. Sorry about that. UTC is the universal time. It's based on Greenwich Mean Time. Then it can give you, down here, maximum and minimum temperatures. So this is the forecast high. This is the forecast low. Or sorry, this is the forecast low, and this is the forecast high. It can give you the temperature at any of those times, and give you the dew point at any of those times, cloud cover at any of those times, wind direction, wind speed. And so each one of these things can then be used in making an accurate forecast. And you can compare model output from one model, the GFS, to another model, the NAM. And so this is a very useful tool that meteorologists have when they make forecasts at a given location. They can compare NAM to GFS results, they can look at other different models, and get a pretty good idea of what the weather is going to do. Now, why do forecasts go bad? Well, so far we've mainly talked about weather models. Weather models are bad because they use approximations and they make assumptions. As a result, they don't take a lot of things into consideration. They leave a lot of stuff out. And each of these models, as I also mentioned, has strengths and weaknesses. As a result, weather forecasting can never be a truly automated process. Because each of these models have strengths and weaknesses, you need humans to interpret those strengths and weaknesses, to take model data and determine, okay, this is what the models are really telling us. This is a good forecast, this is a bad forecast. And so humans are needed. And we'll talk a little bit more about humans and how they make forecasts in the next lecture.